All right, so the first problem that we're looking at was number 36 here. They give us a graph of electric potential versus position, and they ask us to find what is, basically calculate what is the electric field from this electric potential. Right, so for this problem and for all three of these problems, really there's one idea, one real equation that we need to use. So what's the idea that we're going to be using? What's the physics principle, or what's the equation for this problem and even the other one? Or to put it another way, how is the electric field related to the electric potential?
Isn't it the derivative of some?
Yep.
We took the integral to get to there, and then we have to take that.
That's right, right. Well, yeah, if we knew the electric field, we could get the potential from doing the integral, right? And in this case, now we know and this is easier, we know the electric potential, we take the derivative to get the electric field, right? Really, it's the negative of the derivative, right? Because a positive charge will be forced from a higher to a lower potential. So if I now quickly, I'm going to be switching the screen share between this and paper. Okay. So you should have this, and I put a bunch of these equation sheets. So that this is the equation sheet you'll have on the AP test. Not a lot of people picked them up, so I hope you either printed out your own copy or you have access to this. It's on the class website, Google Classroom. But this equation here, right, the x component of the electric field is the derivative of the potential with respect to x. Let me write that out. All right. So if I switch back real quick to the problem, all we need to do is figure out what the derivative is in each of these ranges, and then we can plot them, right? So well, in a straight line like that, or looking at a graph, how do we know what the derivative is from this graph?
Slope.
Say that one more time.
Slope.
Slope, right. So if we look at the first region, what's the slope from 0 to 1 centimeter?
20.
Yeah, 20 volts per centimeter, right? So what would the electric field be? I didn't catch it.
0?
No, the electric field is the negative of the slope, right? Negative dV dx. So
then negative 20.
Negative 20, right? So negative 20 is the slope from 0 to 1.
See.
So if I go down here, I'll make a negative 20. And so down here, right, the electric field is negative 20 newtons per coulomb. Actually, it's not newtons per coulomb because this is centimeters, not meters. So why don't I use the units volts per centimeter? Okay, with that, how we got the first region, we're just looking at the slope and taking the negative. Okay, so if we look at the time or the distance from 1 to 3 centimeters, what's the slope here?
0.
Is 0.
That's 0, right? So what's the electric field?
Also 0?
Also 0, right? So I will plot from 1 to 3 centimeters, our electric field is 0. Maybe I should be using a different color, but that's all right. All right. And then finally, we have from 3 to 4 centimeters. What's the slope and the electric field from 3 to 4 centimeters?
Negative 20.
Negative 20. So that would be positive 20.
Yeah, slope is negative 20, right? It's a negative slope now, right? And you know, everybody knows how to calculate slope, right? Rise over run is also, you're just doing negative 20 divided by 1 centimeter, right? To get negative 20 for the slope, so the electric field is just positive 20. So up here, we'll say that's positive 20. All right, so we have kind of a step function for our electric field in this case. I didn't really line that up very good. All right. And that's really it for number 36, I think. Any questions about that one?
It seems pretty straightforward.
Yeah, this should be. 38 is going to be pretty similar. So let's take a quick look at that graph. I think it's the same question, but it's a slightly different graph. Right, so in number 38, again, it says electric field is parallel to the x-axis, and the potential and it gives us the graph of the potential with position, and it asks us to graph the x component of the electric field. All right, so we use the same idea that the electric field is the negative of the derivative of the potential. And we just take it, step by step, region by region. So for the first centimeter, and I'll stop, flipping back and forth. But what do we have for the first? What do we have for the electric field between 0 and 1 centimeters?
Could I
Negative 30?
annotate?
Yeah. So we have negative 30, right? Negative 30 volts per centimeter. We have negative 30 volts per centimeter for that first, from 0 to 1. And what's it going to be for the from 1 to 2?
Positive 30.
Positive 30, right? Because now the slope is negative 30. So from 1 to 2, we have a positive 30. What about from 2 to 3? Need me to flip back?
0.
Yeah, from 2 to 3, the potential was 0, but the slope of the potential was also 0, right? It's flat. So from 2 to 3, there's no electric field. And then 3 to 4.
Positive 30.
Yeah, 3 to 4, we now have a negative slope again, and it's still the same slope, but negative. So we have another region where the electric field is positive 30 volts per centimeter. And then finally from 4 to 5 is the last one. And what would our electric field be in that very last region?
Negative 30.
Negative 30 again, right? All right, so another step function like that. Are we all right with those two? Any questions? How we got those? All right. The key is to remember the electric field is the derivative, the negative of the derivative of the potential. Ready to move on to number 39.
Yeah.
Okay, so this is pretty much, so we're going to be using the same idea here, right? We're just, instead of graphically, we're looking at it algebraically. And instead of just one dimension, now we have a potential in all 3 dimensions, right? We only discussed 2 dimensions, but you can always we can do this in 3 dimensions as well. So this one gives us a potential, right, as a function of x, y, and z. 5x minus 3x y, x squared y plus 2y z squared. And the first thing we want to do is find expressions for the x, y, and z components of the electric field. Right, and I know a couple you put in your homework that you had trouble understanding how to do this one. So let's see what we can do. So basically, we want to find the x, y, and z components of the electric field if that function is our potential. So here's our potential function again, and we're looking for, let's start with Ex, right? And we're using the same idea, the same equation, that Ex is the negative of the derivative with respect to x of the potential. So, and when we're taking these partial derivatives, right, the rule is, if we're taking the derivative with respect to x, then you can assume that y and z are just constants. If you're taking the derivative with respect to y, then you can assume x and z are constant. So what's our derivative with respect to x going to be of the first term in that? Let's go term by term, of the 5x term. If I take the derivative of 5x with respect to x, what do I get?
-5.
-5 plus 6xy.
Right, -5, yeah, because it's the negative. So we get -5, and then the second term was that you, Mahmoud? What did you say for the second term?
Plus 6xy.
Plus 6xy, right? Because if you hold y constant and you use the power rule to take the derivative of x squared, you get 2x times 3y is 6xy. And then we take the negative of that, so we get plus 6xy. And then what about the third term, the 2yz squared? What do we get for the derivative from that?
Doesn't exist.
Right, nothing, right? 0, because there's no x in there, right? It's just taking the derivative of a constant. So that's our x component of our electric field, right? -5 plus 6xy. If we want to take the y component, now on the equation sheet here, we just have the only equation we have is for the x component. But I think we can maybe intelligently try to guess what the similar equation for the y component of the electric field is. What do you think the y component is of the electric field?
EY equals -dv over dy.
Yeah, exactly, right? And that's got to be true because it doesn't really matter what we name our axes, right? So yeah, the y component is the derivative of the potential with respect to y. So now we assume x is just a constant when we take our derivative. So that first term, the 5x, what does that give us?
Does not exist.
Doesn't exist, right? 0. What about the second term, negative or minus 3x squared y with respect to y?
Plus 3x squared.
Yeah, just plus 3x squared, right? Because we're still taking the negative, and the derivative of a constant times y is just that constant. So we have 3x squared. And then for the last term, the 2yz squared.
-2z squared.
Yeah, right, -2z squared. All right, any questions on that part so far?
Yeah, Mr. Marcus, I'm having trouble understanding why we treat the other variables as what's it called? As constants, yeah.
Well, that's so these are partial derivatives, right? So we're saying so really what we're saying is how does this function change if all we change is y, right? What happens to the value of the function as we vary y, right? And if you're varying y, then changing x, then x is being held constant, right?
Okay.
So if you can kind of, and we'll take a look at some visualizations of this in the future, yeah, you can kind of think if you're varying the y value, and you're holding x constant, right? So you can treat x as a constant because the derivatives. A derivative tells you how a function changes as you change, how the value of the function changes as you change the independent variable.
Right. Okay.
And I know that I don't think the calc classes in our school go over partial derivatives, but if you take calc, 2 or 3, probably in college, you'll see them pretty quickly. Multivariable calculus. I hope that answers your question without having to go into the whole
Sort of.
math lesson. So finally, we just have one more, right? We have the z component. And we do, it's the same thing, right? It's the same thing as with the x and the y. The z component of the electric field is just the derivative of the potential with respect to z. So again, that first term, 5x, doesn't have a z in it, right? So that gives us 0. And the negative 3x squared y doesn't have a z in it, so that gives us 0. And then what do we get for the electric field then from the last term?
4yz.
Yeah, 4yz, right? Because derivative of z squared is 2z, and we multiply that by our constants. And let's see, there's one thing we're forgetting, right?
Positive 4yz.
Oh, do I? This term is.
Oh, yeah, negative,
term
negative.
is right, yeah.
Yeah.
That term's positive, so we want to put negative for the electric field. That's a 4. I don't know why it looks like that. All right. Are we okay with that then?
That's understandable.
You say you do understand it or you don't understand?
I said that is understandable.
Good. So if it's understandable, does that mean you understand it or just it's theoretically understandable?
Well, so I get the premise of, like, if it's in the x direction, you have to use the terms that have the x variable in it. And if it's in the z direction, you can only use the variables that have the z direction in it. Like that makes sense to me.
Right.
If that's what, yeah.
Okay. So let's see now, there was a part B to this, right? So if I go to this again, so what's the magnitude of the field at the point P that has coordinates 1, 0, and -2? So point P is at 1. So basically we want the electric field (1, 0, -2). Let's see how we're going to do that. So how are we going to, any ideas for how we can find the value for the magnitude of the electric field at this point?
You could say E equals like, I think it's the quadratic equation, not the quadratic equation. It's similar to that. I forget the name.
Yeah, Pythagorean. Right?
Yeah.
Yep.
You use that, and then you just plug in your variables and such.
Right.
Like, yeah, like you just plug in all your equations and then you plug the variables in.
Okay. So yeah. So let's find out. So right. So you kind of said, well. So yeah. First we want to find out what our EX, our EY, and our EZ are at this point, and then we would use the Pythagorean, or really the Pythagorean theorem in 3 dimensions to get our magnitude, right? So what is our EX at this point?
-5 plus 6xy, or just 6y.
Yeah, so -5 plus 6, well, 6, no, well, now we're not taking the derivative, right? So we actually need to plug in, right? It's our x coordinate.
0.
Right, so -5 plus 6xy, so 6 times 1 times 0, right?
Yeah.
And so that ends up being just -5. Everybody with me there? So the x component would be -5. The y component, what are we going to get for our y component? So 3x squared, x is 1, remember, so 3 times 1 squared is just 3. And then -2 times z.
-8.
Yeah. Z squared is going to be 4, right? Negative 2 squared is 4 times 2 is 8. So we have 3 minus 8. So EY is also negative 5, right? And then, sorry, I keep moving my paper. EZ, the Z component. Well, what do we get if we plug in negative 4YZ? Where Y is 0. Since Y is 0 at this point, or this is a point on the y-axis, then the Z component of the electric field is 0. So since we only really have 2 components here, we can just use the normal Pythagorean theorem, 2 dimensions. Right? So the magnitude of E is just going to be the square root of negative 5 squared plus negative 5 squared. And what's that going to be equal to?
No, that's wrong. The square root of 50.
Yeah, square root of 50, right? Because 25 plus 25. So square root of 50, that's going to be, well, that's the square root of 25 times 2. So we get 5 root 2. Which makes sense, right? Because if we have a triangle with 5 on each leg, you're going to have 5 root 2 for the hypotenuse. So that's our answer to part B. Any questions about how we got that or anything anybody missed? I think the trickiest thing, right, up here, when we were taking the derivative, you know, you had to take the derivative of one variable and keep the other 2 constant. But down here, when we go to plug in, right, you're just literally plugging in what do we have for X, what do we have for Y, and what do we have for Z. I hope that was clear. I will stop recording now and make sure that I put this up in case you want to refer to it afterwards.